чтобы иметь больше вот этот интернациональный вклад во всех уголках, во всех направлениях студенческой жизни. И вот одно из таких направлений, которое работает уже на протяжении многих лет, является программа «Выдающийся лектор SPE», в рамках которой ведущие мировые специалисты с огромнейшим опытом приезжают к нам сюда в университет для того, чтобы выступить с лекцией и поделиться тем действительно неоценимым опытом, который они получили во время работы над тем или иным проектом. И сегодня вот очередное такое выступление. Я бы хотел представить вам мистера Леджервуда третьего Лероя Уильямса, который проведет лекцию по теме «Разгадка причин низких скоростей бурения при строительстве глубоких скважин». Сразу хочу сказать, что лекция будет на английском языке, поэтому будьте готовы к тому, что, возможно, будут небольшие сложности с пониманием, но мы со своей стороны тоже максимально постарались сгладить этот вопрос, и студенты нам помогли и перевели презентацию, поэтому она будет на русском, но все наше с вами взаимодействие будет на английском. Тем более мы, как международный университет, как никто другой, должны владеть как минимум одним иностранным языком. Ну ладно, это небольшое лирическое отступление, а сейчас я бы хотел пригласить мистера Леджервуда сюда. Пожалуйста.
Well, good afternoon, I guess it is. And it's good to see you all here. Let me tell you a little bit about myself before I get into this lecture. I'm not an expert on drilling in this area or anywhere, even in Russia. My expertise has to do with drilling in general, and as you'll see in this talk. About 42 years ago, I began my career in drill bit research. So we're studying the bit that actually cuts the rock to make the oil well, and studying how to make that faster. When I started a normal, maybe shallow well, 3,000 meters vertical would take several weeks to drill, and it would take dozens of bits. Of course, now we can maybe drill that in a few days with just a few bits. So that's to give an example of the profit of doing this kind of research. And I started, I got to work with Hughes Tool Company when I started, and I worked with some of the people that I'll talk about in this presentation, and they were my mentors. Back when I started, almost nobody had any high-pressure test equipment to test rock, and during my career there have been many machines that have been built around the world to test rock drilling under pressure. So I do want to thank the SPE. Now, I'm an SPE member. It's a professional society of people like me that work for different companies, and we get together and we can share ideas at conferences or write papers that are published, or events like this where I'm going to share with you. So we want to thank the SPE Foundation and the AIME for money to do this. As I understand, the rest of these slides will be in Russian after this. I originally thought we were going to translate this, but with a person. But I hope you can understand my English. I'm going to tell you a story about a scientific investigation that's gone on in our industry for about 70 years, and I'm going to bring it forward to today. One of the major learnings that we made along the way was that the crunched rock material deep in the earth actually has some strength, and that'll be one of the major points of this presentation. People learned, well, let me just go on to the next slide here, which shows some of the points that I'll make. And it's written as a mystery. I'm not sure what it says in Russian, but that was to get people's intrigue, because in fact it is a mystery. But we can be misled in forming hypotheses if we think of rock as a brittle material, and because we experience rock as a brittle material, but deep in the earth it's not brittle. It has totally different mechanical properties. As I said earlier, we've learned that even the crushed rock material, that would be like sand, has a significant amount of strength. And the mud that we use to drill with, the oil-based or water-based mud or heavy mud, affects the rate of penetration a lot. So, and then finally, at the end, I'll try to answer some questions about what the focus for the future should be. I'm near the end of my career. I'm actually hoping that maybe some young person here will say, "Wow, that's interesting," and then start a career from that. So first of all, this is making the point that I said earlier that we experience rock as a brittle material. I wouldn't like to have brought a piece of rock in here and just break it for you. Maybe you've had that experience, but I didn't want to pack that in my luggage. Or maybe you've had the experience of taking a chisel and hitting on it with a hammer and then the rock breaks. And this is what we mean by brittle material. So we think of rock as being brittle. One thing we're going to see a long time ago is people made hypotheses about what happened down hole. They assumed that the rock was brittle, and that was a mistake. So basically, rock is made up of hard grains that are glued together. This is a piece of sandstone, and you can imagine it like take beach sand and somehow glue all the grains together. That's what the rock is, a granular material. And there's two basic classes of bits that we use to drill rock these days. One would be what we call a drag bit, and it rotates as shown in the picture there, and part of the bit just scrapes on the rock and shears it away. There's an old bit shown on the left. That's actually a bit from a little over 100 years ago, and then the one from today. And then the other kind of bit is a rolling cone bit, or sometimes it's called a tricone bit. And those cones on there are just wheels that can rotate freely. And so as you put a lot of force on the bit, or we call it bit weight, as you put a lot of weight on the bit to make it drill, that force is concentrated on a few teeth and it crushes the rock. So two kinds of bits. We'll talk about each of them a little bit. Again, the one on the left at the bottom, that's one from about 100 years ago that a guy named Howard Hughes in the United States invented, and that was the beginning of Hughes Tool Company. So let's think about what would happen at atmospheric pressure, first of all, if we indented a rock. And so the blue thing here is meant to represent a rock bit tooth, and the sort of brown or amber color up there is meant to show the rock. As the tooth begins to penetrate the rock, first of all, it crushes the rock immediately under it, as shown in that red zone there. And that crushed material is like a plastic material that wants to flow. It has less strength than the elastic material, but it's constrained by all the elastic material around it to keep it from flowing. And then as we continue to indent, if we get the pressure high enough, it can make a chip. It will drive a long crack that will start there in the crush zone and propagate off the surface, and then big chips of rock will fly away. And this is, if we could just watch drilling in a laboratory, this would be what we'd see. The same kind of thing happens with the drag bit. This the blue here is meant to represent a diamond cutter. It's moving from left to right in the image, cutting rock. As it advances from left to right, there's a crush zone, again shown in red, that's plastic material that would like to flow, but it's constrained by the elastic material. And then once the pressure gets high enough, we'll drive a crack, a big long crack. So, and then the piece will fly away. And the piece that flies away is a little chip of rock that you could study and see the morphology of what it looks like. So this is a picture of a test facility from 1955. Somebody asked me earlier today how I got started in this area. And the answer was that my father had been in it before me. He worked for Exxon and did drill bit research. And when, about the time I was born, 2 years after I was born is when this picture was taken, but about the time I was born, he came to Houston and actually used this very machine and some tests they were doing back in that day. But that's not a part of my presentation, that's just a personal piece of information. But I like this picture because it was part of a recruiting brochure from the 1950s where this company was basically saying, look how great we are, we've got this great lab, why don't you come work for us and do research for us. And at that time they assumed that there's a big rock down there at the bottom that you really can't see. There's a drill stem coming from the ceiling that you can see, that you can put a bit and rotate, you can drill in this big rock. And then the water all around there is to clean the rock. But they assumed that this sort of atmospheric pressure drilling would be representative of what happens down hole. if you were to read the English here, the first part of that, it talks about how it simulates downhole conditions as far as possible, let's say. But about that same time, people began to learn that if you retrieved a core from deep in the earth that you had been drilling, and then if you drilled on it in the laboratory, it was much easier to drill in the laboratory than it was to drill when it's deep in the earth. And so that raised the question, well, why is it so hard to drill when it's deep in the earth? And that's the mystery that I talk about. There's still some mystery left to it. We understand a lot better today than we did back then. But they recognized that the rock was harder to drill if it was in the earth. And the question is why? Answering that question is pretty much what I'm going to be talking to you about in this presentation. So even back then and way before then, people had realized that rock was a pressure-sensitive material, people who worked with rock. And this guy here was one of the heroes that started using this sort of analysis. And so in the 50s, when the oil field researchers started getting into this, they used this type of analysis to model the drilling. So this is going to talk about some tests that were done. In 1955, a guy named Bob Cunningham, and he was the person I worked for when he was old and I was young. But anyway, he built this machine that's shown here as one of the first high-pressure microbit test machines. And it's because they realized they needed to test rock under pressure to make it act like it is downhole. So he built this machine that would use small bits, as I'll show in a moment. And he actually did tests on it to measure the rate of penetration, meaning how fast you can drill in the rock. And then he also modeled the rate of penetration with the Moore Coulomb theory that people were using at that time. This is a little more information on the test. You can see the microbit at the bottom. That's about 3 centimeters. And so it's much smaller than an actual bit, because back in that day, I see that the graph on the right actually has a little bit of glitch to it. I apologize for that. The brownish looking stuff is the rock. It's kind of removed. But at any rate, we couldn't build huge pressure vessels in those days. Didn't have the money, or I guess the technology. So they built a small version. And yeah, so they use this Moore Coulomb model of a plastic material, or to explain what they hoped would explain the mystery. And I want to take just a moment and talk a little bit technically here about what the Moore Coulomb model represents. We can plot it in the space of hydrostatic stress on the horizontal axis or shear stress on the vertical axis. And a circle that has its center on the horizontal axis represents a stress state. So imagine if we did a test where we took a cylindrical rock specimen and just squeezed on it axially and kept raising the pressure until it broke. And if we measured the force at which it broke, we'd call that the confining, well, it'd be the unconfined compressive strength in this case here. We call it compressive strength is the word I was looking for. And we can plot that here by plotting the confining pressure at the left on the horizontal axis and the actual pressure that we found at which the rock fails. And then we can draw the circle in there as I described, and the height of that circle represents the shear stress required to fail the rock. Well, now that was for an unconfined test. Let's imagine we take the same piece of rock, and this time we put pressure all around it, and then we increase the axial force to find out how much force it takes to fail it. What we'll find is it takes more force to fail the rock when it's under compression. And so we can plot again the confining pressure shown at the left, and the measured compressive strength shown at the right, and the circle a little bit higher than it was is a bigger one, meaning more shear stress is required to shear the rock. And we can even take this to higher pressure, and then we'd find that the rock gets even stronger, and the shear stress required to fail it would be even stronger. So we can do a bunch of tests on pieces of rock at different pressures, and get a circle from each one of these tests, plot the circles together as shown there, and then plot through it what we call a failure surface. And what that failure surface means is if the stress grows big enough such that it touches the failure surface, then it's defined to be failure. And we can put mathematical parameters on this so that we can solve these things mathematically. And this is basically the the equation that Cunningham used, and I'll show you some of his results. And it's still the basic equation that we use today, maybe in a slightly different form. Maybe we use a Drucker-Prager material rather than a Moore material, but it's a similar sort of thing. The theme of this is that this model here does not explain everything, and so there's still some of the mystery left. I believe that should say, since I can't read it, that well, actually I don't know what it says. There's an example I like to bring, and I would like to have brought this with me, but I didn't know if I could get it through security. What it is a bunch of ball bearings glued to a board. So there's two boards there, each have ball bearings glued to them, and then over on the right, the two are put together where the ball bearings touch each other. So since I don't have that here, I want to just use this image and put that together. This example here, is similar to the way rock behaves. If we put a shear stress on this thing and push it, we can push it and we'll find out that there's a volume expansion as we do. And there has to be, because the grains need to move apart a little bit and to move past each other, as is shown by this simple example. If we put a weight on top of this and ask how much shear stress, well, it takes more shear stress to fail it because the weight resists that. But there's still a volume expansion, and the idea that the rock expands as you shear it is going to be really important in this discussion, so you need to remember that. So this shows that we have volume expansion, and that the higher shear, the weight, which it says in English there, is similar to the confining pressure. Remember I talked about doing a test and putting pressure all around it. The weight is like that in this simple example, and the shear force is like the shear force. So there's a lot of different pressures downhole, a lot of different stresses downhole, and I want to list them here. There's the overburden stress that's basically due to the weight of the earth. When you get deep, you know, maybe 3 or 4 or 5,000 meters, there's a lot of weight of the earth above it, pressurizing the rock. And there's a confining pressure, people usually call it. It's a lateral stress that's usually somewhat less than the overburden pressure. And then as we drill the hole, we fill up with mud, and the mud is very heavy and made so on purpose, as you know, so that the gases and things in the earth won't blow out. To keep everything together, but the mud is usually lighter than the overburden pressure. And finally, there's the pore pressure. So there's all these different stresses, and the question that becomes, and the question for Bob Cunningham back when he did his first research in the 50s, is which of these pressures governs the rate of penetration? They did a lot of tests with that microbit rig, and they varied each of these independently, and what they found was that what they called the differential pressure is what governs how fast the bit drilled. And the differential pressure is the difference between the borehole pressure and the pressure in the pores. As the differential pressure gets high, the rock becomes more difficult to drill. Now, many rocks are permeable, which meaning that fluid can flow into the rock, and we don't want that to happen in the earth. We want the fluid that we put in the borehole to come back out of the borehole, not go into the earth. So we formulate drilling muds such that they inhibit that, and they form a filter cake around the edge. So it seals off the rock, the permeable rock, to prevent drilling mud from going into the formations. And that's very necessary for drilling, but it also is going to turn out to be detrimental for the process of failing the rock, as we're going to discuss in this lecture. So these graphs here are two graphs from Cunningham's thesis in the 1950s. And you can't read those axes, so let me change them here. Somebody did a very good job of I know this was a lot of work, and I thank somebody for translating into Russian. But the horizontal axis is the pressure that's applied to the test specimen, and the vertical axis is the rate of penetration reduction. So let's just look at a couple examples here, and I'll explain a little more. There's two different rocks here. I just showed you of them to give you an example. If we look at the left graph, at a pressure of 0, being all the way to the left on it, you see the rate of penetration is 1, just by definition. And then if we go up to about 7 megapascals, we find that the rate of penetration drops to 60%. And so that's the drop, and you can see in red there. That's what they actually measured in their test machine. But the theory, the more Coulomb theory they were using, didn't predict as dramatic of a reduction in rate of penetration as they actually measured. And so that raised the question of why. And Cunningham ended his thesis basically pointing all this out, just making the observation that the Moore Coulomb model only explains part of what's going on. There's something else going on that remains a mystery. So at that point, a lot of researchers around the world, and if you ask a question about like SPE, for example, what value is it, even SPE existed in that day, and all these researchers would publish their data in SPE papers so they could share the data. But at any rate, a lot of people started working on this problem. Here's a couple of guys who tested in 1958. They built their own microbit rig, and they were wanting to find out what's responsible for the increased reduction in rate of penetration. And they came up with a theory that they called chip hold down. They imagined, and this is where I think they went astray, they imagined that under pressure a long crack grows like it's shown in that image there, but under pressure the chip can't go anywhere because there's fluid pressure holding it down. So the fluid pressure is like the borehole pressure, and there's a filter cake shown there. And so you can imagine if there's high pressure on that chip, it'll be holding it in, and if we're talking about pressures, of 100 megapascals or something, there'd be a tremendous force holding that chip in place. So they call it chip hold down. I'm going to tell you later that this is not what actually happens, but it's the hypothesis they came up with. We can't actually observe physically what's happening under pressure, so people had to do tests and hypothesize. This was Feenstra and Van Leeuwen, I believe, but they plotted their results shown here, and similar to Cunningham, they showed that the theory, the Moore theory, only explained part of the reduction, and they claimed that the rest of the reduction was due to this thing they called chip hold down. And then another researcher began to work in the 60s using the first full-size test facility. So in this facility, they could put a full-size drill bit, put a relatively large core of rock in there and pressurize it and drill on it. Today we have machines much bigger than this, but this was for their day. And they found that the rate of penetration reduction was rate sensitive. And this here we have pressure across the bottom, and the vertical axis is the rate of penetration reduction. And what they found is if they did a test at 27 RPM, if you start there at zero pressure, you see the pressure rising as you move to the right, but it reaches some limit and it just stabilizes at that point. And they found that if they go to a higher RPM, it would follow the same path of increase and reach some other highest value, and similar on up to 315 RPM. So there's something rate sensitive, the speed at which you cut the rock, they're finding out has something to do with it. Using the idea of chip hold down, they came up with a hypothesis that you've got to get some fluid flowing in there under the chip, like shown as bold green arrows, to equalize the pressure so the chip can go away. And they hypothesized that at lower speed, you had more time for the fluid to get in there, and so that's what explains the graph on the previous page. So when people started studying drag bits, which would have been a few years after what I've been talking about, they noticed that drag bits, and so shown here would be a diamond cutter moving from left to right, and the brownish or maybe orange on the board material is the rock. And we observed that it makes a sawtooth-shaped chip. Let me go back to that picture here. So if you see right here, it looks like a sawtooth. That's what I'm talking about, sawtooth-shaped chip. These are some actual chips that were from laboratory tests to give you an idea of what they look like, and some of them you can kind of see the sawtooth shape pointing at us there. So people assume, and I was involved in it by this time, this would be the 1980s, that as we cut with a drag bit, we're doing something over and over. We're driving a long crack, like shown there, and then that chip moves up a little bit, and then the cutter advances, and we drive another crack, and it moves up a little bit. And so you get a stack of chips of rock. That was, again, the hypothesis. and people believed that for quite some time. But back in actually not too long ago, about 10 years ago now, a guy named Ron Bland discovered that there's no stack of chips. The material is entirely crushed and extruded. So I've changed it to sort of a tan color there to represent the crushed area. So as the cutter moves from left to right, we crush all this and then we extrude it up in that direction, and it comes out in the sawtooth shaped type chip. One way we know this, a simple way, is you can take these cuttings after they're made and you can grind them up in your finger. And if there were stacks of chips of unfilled rock, you wouldn't be able to do that. You break it into the stacks, into individual chips. But it breaks into small material, and Bland quantified this for both tricone bits and PVC bits and showed that they both crush the material entirely. So this is not what happens here, this sort of brittle failure that we might think about rock, long cracks being driven in it and big chips coming off, but rather there's the crushing and extrusion type process that goes on. And that's true not only for drag bits, but for the rolling cone bits, and so it's not as shown at right, but as a cutter goes in, it actually crushes a large volume and extrudes just a small part of that. So more recently we've done analysis of this, and this is an image from a discrete element analysis. Maybe you're familiar with that, but the amber colored balls or orangish color are representing grains that are glued together. In the mathematical model, they have a tensile strength, they're glued together. And then as the cutter, there's a cutter on the left that will be advancing. Actually, I can put part of this here. So the amber balls, as I said, they're representing the original rock that's glued together, like I said in about the first or second slide. And these blue balls are the cutter is advancing, and it's breaking the bonds in the amber balls. And once the amber has broken, once a grain of the amber has broken all of its bonds, the computer changes the color to blue. So we can just see what the crushed zone is. The blue is the crushed zone. The black dots represent the crusher boundary condition. That's actually a relatively complicated thing to know where the pressure is applied, but there's pressure being applied not only to the rock, but also to the cutting that's extruding up there. And finally, there's a PDC cutter moving from left to right in this image. Excuse me. The same thing happens with modeling the tricone type cutter. So again, you can see a large volume that's crushed, and only a very small part of the rock that's actually removed in the indentation process. So when we set up a model like this, we know the rock properties. We can take a rock and do a test like I mentioned earlier, and that would be the properties of the amber color balls over there. And we know the properties, the mechanical properties of the cutter, but this blue material here is now a third material that we don't know its mechanical properties. And if we go with our gut, we're going to say that the blue material is probably relatively weak because it's crushed rock. It's just like a bunch of sand. And but that's where we would be wrong if we assume that. And so the slides going forward are going to, actually that shows that in English. And anyway, I guess it'll revert to Russian as we go on in a moment. But as we, in order to understand how the crushed material can have strength, we need to talk about dilational hardening. That's a big word. Dilation just means something dilates, it expands. And you remember when I talked about a rock, if you shear the rock expands. And then hardening means when the rock dilates, it makes it appear to be harder. So in this picture here, the blue is a drag bit moving from left to right. The little fish in it is unfailed rock. And there's borehole pressure and there's pore pressure. Remember that the difference in those two is what strengthens the rock itself. But we're interested in the strength of this material in the crushed zone. And what is that? And there's a pore pressure in it. So we really need to talk about the differential pressure between the borehole pressure and the pressure in the crushed zone to be the pressure that strengthens the cutting. So go back to the idea that as we shear the rock, it dilates, and all the dilation or all the volume expansion is happening in the pores. So the pore size is growing quickly. And as we do, we drop the pressure. You see the little the blue arrows are getting smaller. And it's been shown that we frequently, it's common to drop the pore pressure to 0 in that area due to the dilation that happens when you shear it. And so the differential pressure in the cutting is the borehole pressure minus 0, and so it's the entire borehole pressure, which is basically the highest it can be, strengthening the cutting. So this shows the counterintuitive result that as we shear the rock downhole with pressure, if the mud is right, as we'll see in a moment, then it makes it very difficult to drill. So if we take the cuttings after a test, as shown here, this is some shale cuttings. But if we had some we could play with, we just see it's squishy. It's real weak as we would expect it to be weak. And we're tempted to imagine that that's the same kind of strength that has downhole, but that's not the case. And if we want to evaluate the strength of the cutting, we can't use the cutting like was shown in the previous slide, because that cutting was formed during a cutting process, and then the test was depressurized and opened up, and somebody got the cutting out, and several minutes has passed, and a lot of fluid has gone into the cutting, making it weak. So by the time we can look at it, it's already weak. So we really need some way of investigating the strength of the cutting at the instant it's created, because it only has strength for a very short time at the instant it's created. And the reason it has strength for a short time is because as time passes, fluid can get in there and raise the pore pressure on the cutting and weaken it. So we built a special bit to try to get a handle on this, and it's shown right here. And it's built with some wire rods protruding in the path where the cutting is going to flow. And we made some of the rods of copper, some of bronze, which will be stronger. Mild steel is a little bit stronger, of course, and then hard steel, which is the strongest. And what we wanted to find out was which of these would the cutting be able to bend. And we actually had a whole bunch of weaker rods than these that we were going to test too. But if we could find out which rods it will bend and which one it can't, we get an idea of the strength of the cutting at the instant it's created. And what we found was, in tests of Catoosa shale, which is not a very strong shale, the cuttings bent all of the rods. I know it's hard to see there, so let me color the original position of the rod is shown in red, and the deformed position of it is shown in green. In the left image there, you can see that cutting, actually the cutting grows normal to the surface, so in this direction, so that's actually bent in the right direction for the cutting to be bending in. So we can't calculate exactly with such a crude test what the strength is, but we can make crude calculations, and we can find out that the cuttings, at the instant they're created, have a strength that's on the same order of magnitude as the rock itself. So it can be very difficult to shear. I have another toy I like to use. I wish I had it here with me to demonstrate how crushed material can have some strength. And what this is a balloon filled with sand connected to a syringe. And if we had that here, and if I could show it to you, you could squeeze the balloon, and when the plunger of the syringe is in, you'd find out it's very easy to deform the sand that's inside the balloon, and when you take your fingers away from it, it returns to its original shape. But if we pull the plunger out to pull a vacuum in the pores between the sand, then we find that it's very hard to deform it with our hand, and once we take our hand away, it maintains the deformed shape that it had. So what's going on there is the yellow here represents the pore volume, and we're dropping the pressure to 0, and all around the outside there is 1 atmospheric pressure. That's shown at 14.7 psi, but it means just basically atmospheric pressure, and that's holding the grains together, just like that other example I had of 2 blocks that are held together by a weight, and that's what gives the material its apparent strength. And this is only 1 atmosphere of pressure strengthening the material, which is not particularly high. Imagine if we could take this test to the bottom of the borehole where we had maybe 100 megapascals of pressure, and if we could squeeze on it, I suspect we'd find that it would be impossible to squeeze. It would be extremely strong, but we can't experience that personally. Maybe that's what that slide right there says. Another important question is, where does the energy go during the cutting process? And from a model like this discrete element model, we can answer that. We can just ask the computer and answer that question. And so the question is, how much energy goes into failing the original elastic bonds between the grains, and how much energy goes into extruding the crushed material? And excuse me, let me go back. So what the analysis showed is most of the energy in cutting actually goes into deforming the crushed material, not into breaking the original bonds. So it's not so much the strength of the original bonds, it's something about the crushed material itself that makes it hard to shear. A guy named Rafashian did some tests about 10 years ago, and he was testing the same sort of thing as I've been describing all along. Across the bottom is shown the pressure, and the vertical axis he's quantifying it with specific energy, which is a measure of the strength of the rock. But he showed the same kind of thing that people had shown before, is that the Moore-Coulomb model only predicts a certain amount of strengthening, as shown in blue there, but the measured strengthening is much higher. The important thing about Rafashian's work, and why I wanted to show it, is he showed that the rock material becomes significantly stronger at a relatively low pressure. At 1.4 megapascals, the material has already got its strength. So it doesn't take a lot of pressure to change rock from a brittle material to ductile material. Now we've made a lot of points. I want to review them here to get them all in our minds before we go ahead. First of all, atmospheric pressure, which is the way we normally experience rock. Rocks are brittle and they form chips of rock that fly away. But when the confining pressure is higher than the pore pressure, the rock becomes ductile and we crush it and we extrude it. And the strength, the thing that governs the strengthening of the rock is the differential pressure, the difference between the borehole pressure and the pore pressure. We've shown that the process of shearing the rock can actually make it stronger because it dilates the rock, which drops the pore pressure, which increases the confining stress on the cutting. We've shown that the strength of these cuttings is high at the instant that we make the cutting, and we've shown that it doesn't take a lot of pressure to cause the rock to be ductile. And finally, most of the energy expended down the hole goes into extruding the crushed material, not into breaking the original rock. So, mud is very important, and I'm calling it a co-conspirator here. I want to talk about some tests that were done by a joint industry group, and this is reported. By the way, every place in here that I've shown the name and the date after it is a paper, an SPE paper that you can get and look at if you're interested in learning more. But these tests were done by a group of companies together, and they reported them in a couple of papers shown there. But this is a full-size test facility in which we today can put a pretty large pit and pretty large rock inside of it. They did many tests, and I'm only going to show you some of them here. In all the tests I'm going to show you, the bit is a 15 centimeter bit. The confining pressure, that would be the borehole pressure, and the pressure around the rock is in the order of 76 megapascal, and the flow rate is well shown there. So the flow rate's the same, but the point is the bit, the pressure, the flow rate is all the same. And what they're going to change, and what I'll show you, is they're going to use just clear water for a drilling fluid for the mud, and then they're going to use a clear base oil for a mud, and they're going to use a weighted mud, a 1.32 specific gravity mud. I don't know that a value in the kilograms per meter cube. I'm sorry to say that, but that'd be about 30% heavier than water, or maybe 50% heavier than water, and then a 1.92 specific gravity oil-based mud. So the question is, changing the mud, does that change the rate of penetration? And so here's the answer. So this is these are plots of data from Carthage limestone, one particular rock, And the green plots there show the rate of penetration that they got for using clear water as a drilling fluid. And so at 67 kilonewtons of a bit weight, they got about 9 meters per hour of rate of penetration. But then if they went to the water-based mud that was made heavier, the 1.3 specific gravity, they found that they got lower values as shown by the X's there. So in this case, the 67 kilonewtons only gives us a little bit less than 6 meters per hour. And when they went to the 1.9 specific gravity oil-based mud, so even heavier, they got lower values, and 67 kilonewtons gave them only about a meter per hour. So, you know, you'd say, well, why don't we just always use water because it drills faster? Well, the answer is the water would flow into the earth, as I said, and we have a problem then because we need to keep the fluid in the borehole. So we make our muds so that they form these filter cakes on the wall of the hole, and that's for a good reason, but it also turns out that the mud has an adverse effect on the drilling as shown here. So this is similar data for another kind of rock, Mica shale. And we're comparing here the base soil showing the oil weighted with weighting material. And so for the base oil at 67 kilonewtons, they got almost 24 feet per hour, but by weighting it up, making the mud heavy, it's only about 5 meters per hour. Again, you might ask, well, why do you want to make the mud so heavy? And you probably know that maybe you can have some really high pressure gas or something down in the earth, and you have to have high pressure in the borehole, so we make the mud heavy to hold things together. This is one last example, crab orchard sandstone. So the first one was the limestone, the second was the shale, this is the sandstone, and you can see the results for clear water and a water-based mud that's a little bit heavier and an oil-based mud that's even heavier. So a very dramatic change in that. We're almost not drilling at all in the case of the heavy oil-based mud. So why? The question is, why would the mud properties have such a big effect on the rate at which we can drill, as shown here? And we think the answer has to do with how much the fluid can invade the cutting. So shown there in green arrows would be the borehole pressure all around the cutting, and then of course there's a pore pressure. If the fluid can get into the cutting on a time scale of drilling, which is a pretty short time scale, then we'll weaken the cutting and it'll be very easy to drill. So like with clear water, the fluid can get in there and the rock is easy to drill. But if we make a heavy mud, then that creates a filter cake on the cutting itself, and strengthens the cutting, and the cutting will be very difficult to drill. That's a current hypothesis, let's say, as to explain why the mud has such a profound effect. So what does all this teach that we've talked about here? And one is that we need to make sure that our models are appropriate. So engineering is all about coming up with a model, whether it's a mental model or a mathematical model or something like that. But the model needs to be similar enough to the thing we're interested in to be of value for us. And I've shown you that a long time ago people had a mental model of rock as under pressure as driving long cracks and making big chips and the chip being held down. But that was the wrong model. And we learned later on that the rock is entirely crushed and extruded as shown at the bottom. Pressure is the villain, as the English said, I presume it says there in Russian. And if there were a way to make the pressure zero, then we'd drill very fast. And that's why underbalanced drilling, for example, is faster than balanced drilling. Another example of that is a long time ago, one company built what they call a pressure fluctuating tool. And so if we imagine a deep well there with a high pressure in the well, what they found is if we vary the pressure between 0 and twice the value, so then if we do that, then the drilling will be fast like the pressure was 0. So apparently the pressure doesn't have to be 0 for a long time. They weren't able to make this pressure fluctuating tool work reliably in the field, and that's why it's not used today. But it was shown that if you can vary the pressure and make it drop to 0 periodically, the bit will drill fast. We've shown that the mud makes a filter cake, and that, of course, we need that filter cake for good reasons in the borehole, but it also makes it also makes the cutting stronger and makes it more difficult. And finally, I showed you that Cunningham used this more Coulomb model back in the 50s and recognized it doesn't explain everything. But the sad thing is it's pretty much what we still use today. And so there's a big need today to understand what it is about the rock that we need to be measuring. And it probably has something to do with the crushed material itself. So the sizes of the crushed material, the angularity of it, certainly chemical issues would come in, the reaction between the cutting and the rock, and certainly the permeability of that. So those sorts of things are probably the way we should look in the future as we try to develop a more fundamental model. So there really is, I think this says that we need fundamental models, and I believe that's what it says. But there's a need, and so even in a university like this, that's a very, very interesting question and a very real question for drilling that somebody needs to answer. So I've shown you that there were references, and so the references are shown here. I'll just go through them quickly. If you're interested in this, this presentation is available to you here, and you can dig more deeply into the data shown there. And also, the SPE would like your feedback on whether this sort of seminar was valuable or not. SPE.org/DL, there'd be a questionnaire you could answer if you wanted to do that. So that's the end of the talk. Do you have questions or comments about this?
Okay. My name is Aziz. I actually major in public relations and advising, so I'm not really familiar with the terms. But from the lecture, what you said was like most of the theories and researches that were done actually in the history that they were not public knowledge. So I wanted to know at what point in your career did you come across the theories and researches? Like at what point in your career did you get to know about these researches?
When I started in 1976, Bob Cunningham, as I said, was an old man, and the chip hold-on theory was very, very common then. The idea that a PDC cutting makes a stack of chips, that was common in the 1980s, and it was really in 2007, I guess, when, which was only 10 years ago, that Ronald Bannon showed that the material is entirely crushed, and about that same time I did these creatable models that we've shown here. So that's just 10 years ago now, and everything I've shown here is described in the papers that are listed.
It's public knowledge, right?
It's public knowledge, yes. Yeah, everything here is public knowledge. Now, like for a person like me working for a company, the company wants to have proprietary things, and we do, but all of this stuff is basically just simple physics, recognizing there's an issue you need to understand. And the better you understand it, then the better you can make a bit of a living faster for some company and sell it and make money.
Thank you very much.
I hope I wasn't too far from the microphone.
No, it's fine.
Yes.
Thank you for the opportunity. Thank you very much for the presentation. My name is Benjamin Chisholm, and my question is, what's most likely the cause of a pipe damage during the drilling process? Can the cuttings be strong enough to cause any damage?
Can it be strong enough to have no damage? Is that what you're asking? Yeah, there is, I've oversimplified some things here. If you have a relatively weak rock, then it will go to crushing more quickly than a really strong rock. If you take granite or something like that, like a basalt, then you have to go to higher pressure before you see the transition between chipping and cutting. At atmospheric pressure, people observed a long time ago that if you take a low depth of cut, so this is the rock here and we're cutting it not too deeply, that will just grind all of the material. That's the term they'd use. If we take a deeper depth of cut, this is the atmospheric pressure, large chips will be made. So you hear people talk about grinding the rock or chipping it, and asserting that chipping is better. And of course that's true. But the real unknown question is, as you put it under pressure, is there some depth of cut at which you can cause a chipping? And I think the answer is no from the modeling that I've done, but it is an important question. And so, but I think if I understood your question, the answer is that in strong rocks, they will persist in brittle failure to a higher under pressure than weak rocks. Yes?
My name is Martin. How is it possible to make pressure in the depth of a borehole is atmospheric pressure? Because there are under the end of the borehole is the air, which makes the pressure too.
Okay, you said air.
Air. So it is the end of the borehole,
yeah.
And upon it's the air, so this is the surface.
Okay, I'm not sure I understood exactly that, but there is a kind of drilling called air drilling, where air is used as the drilling fluid, if you say. And air drilling is typically very much faster than drilling with mud. But were you saying that the pressure of the air is on top of the pressure of the mud? Is that what you're saying?
So, atmospheric pressure influences on the surface of the air, but there is, in the place of the borehole, there is some air in the borehole.
Air?
Air, yeah, which makes a pressure too. So, I think it's,
to the degree that there's air in the borehole or in the mud, then the mud would be lighter by volume, and it would, we need to keep it to be a certain weight to drill successfully.
Okay.
Anything else?
Okay, я бы хотел поблагодарить тогда за лекцию. Спасибо большое. Если кто-то в индивидуальном порядке хочет пообщаться или задать вопросы, пожалуйста.